My name is Dr. Robin Nelson, and on behalf of the NSF-NHERI Network Communication Office, I would like to welcome you to the third session in our NSF-NHERI Professional Learning Community webinar series. As a friendly reminder, please make sure that you are muted while our presenters are presenting, and please look for information. You'll receive an email after today's webinar sharing facility resources, contact information for each presenter, and a survey to share your feedback. In this third session, we're going to learn more about NHERI Rapid Facility from the University of Washington from its ECO Director, Laura Lowe's, followed by the NHERI Large Mobile Shakers at the University of Texas at Austin from its co-PI, Brady Cox. And then we will hear from Arindam Chowdhury, the PI and Director of the NHERI Wall of Wind at Florida International University. And we will conclude with the NHERI Wind Research Facility at the University of Florida from its PI and Director, Jennifer Bridge. But before we begin, we want to just share the format for today's webinar. After each presentation, the facilities representative will hold a short Q&A session. At that time, we invite you to enter your questions in chat or raise your hand and we'll call on you so you can share your question. If you have further questions after today's presentation, we really encourage you to reach out to each of these presenters and to the facility. They really do look forward to answering your questions about their resources, the capabilities of their facilities, and how you can incorporate them into proposals moving forward. So with that, I know we are eager to begin.
Oh, audio devices, what is going on?
Again, I'm going to make sure that everyone that's come in is muted. Please make sure if you have not muted yourself that you go ahead and do that. Thank you so much. We are going to start again with the NHERI Rapid Facility and Laura Lowe's. Laura Lowe's is a professor of civil and environmental engineering at the University of Washington, where she holds significant leadership roles within the NHERI SIM Center and the NHERI Rapid Facility. She earned both her PhD and MS in civil engineering at UC Berkeley and a BS in civil engineering from the University of Washington. As a leading expert in structural and earthquake engineering, Dr. Lowe's research focuses on enhancing structural engineering practices, particularly in the area of earthquake resilience. She integrates numerical simulations with laboratory testing and field data collection to advance this field, and her efforts have resulted in the development of various component models that effectively simulate the earthquake behavior of buildings and bridges. These models include nonlinear response assessments for concrete beam column joints and columns, along with guidelines for the design and evaluation of concrete structures. Furthermore, Dr. Lowe's is a fellow of the American Concrete Institute and is actively engaged in multiple ACI committees aimed at advancing engineering standards and practices. Welcome, Dr. Lowe's.
So I am here presenting on the NHERI Rapid Facility at the University of Washington. And the goal of the Rapid Facility is to enable transformative research by providing investigators with the instrumentation, software support, and training needed to collect, process, and analyze perishable data from natural hazard events. And this kind of gives you an overview of the equipment on the left and some of our in-house support in terms of the data processing infrastructure that we have, and your ability to come to the University of Washington and work with people to process your data. And then probably most importantly, the hands-on training that we offer. And so our flagship training event is a summer training for approximately 4 days on the University of Washington campus in July, when it is actually really nice in Seattle. This is the Rapid Facility Leadership Team. Joe Wortman is the director, and Jeff Berman is the operations director, and Mike Olson is our technical director, and they bring many, many years of experience collecting data in the field and processing those data to generate information that can be used as part of your research. I am the ECO director for the facility, and recently the facility has expanded. I say recently, in the last few years, to include also a significant public health and social sciences activities. And Elena Austin is our public and environmental health lead. Nicole Arad is our social sciences lead. And then we have affiliate faculty at UW and across the country that provide expertise in various hazards as well. Kurt Gurley, Jen Irish, and Ann Bostrom. Probably most importantly or most important to your activities using the facility are our staff, and we have incredible staff to provide expertise on both planning out your reconnaissance activity, figuring out what equipment you need, then helping you to figure out how long you need to be in the field, how many people are going to help you or need to help you support your data collection, helping do some preliminary processing of your data, and then helping you to figure out, and we can also train your students to do processing. And then finally, making sure that your data are done, the initial processing is done, that your data are available to you, and if the data are ready, we'll also then upload them to Design Safe and then provide you an opportunity, obviously, to publish that, but doing that first step of getting your data to Design Safe as well. Our operations manager, Mike Grillo, has a good understanding of all of the tools and a significant background in field work. Ezra provides tremendous expertise on sort of doing the processing, especially with the point cloud data. Jack is our exposure and health team lead and has experience with, knows all of the instrumentation and lots of field experience. And then Andrew, Julia, Alex, and Tim and Matthias are going to head into the field and support you in collecting data as needed. And recently, Barbaros Setner has joined our team as an AI applications expert as well. So helping you to use AI to process some of these large data sets. And all of these individuals, well, primarily Mike and Ezra, Jack, can help you figure out sort of what equipment you need to take into the field, what kind of how much time you're going to need to collect the data, or how to prioritize your data collection, and then again support you in the field doing that. This is showing some of the instrumentation that we have. So we have 12 drones that can take a variety of payload, from multispectral cameras through to just high resolution cameras. We have 5 terrestrial LiDAR units that provide both very high accuracy as well as large range. We have total stations and GNS systems so that you can make sure that your data are located globally. We also have accelerometers. We have high resolution and multispectral cameras and hyperspectral cameras. We have pressure sensors so you can get flow depth and surge height from hurricane-induced flooding. And then we have multiple street view systems that enable you to collect large data, point cloud, or large image data sets that can then be used to generate point clouds. Some of our newest equipment is health and exposure instrumentation. This enables you to look for contaminants in the soil, to do water testing. We have some water sampling systems that can be drone mounted, so you can fly your drone out over the lake, get a water sample. We have the drone mounted hyperspectral imaging. Hyperspectral imaging collects essentially images in wavelengths that go beyond the visible, and you can use that to detect chemicals in the environment. Recently or currently, we're looking at using that. I've personally been involved in a project that's using it to look for corrosion products, but you can look for a variety of different kinds of contaminants. The Bruker system enables you to do some in-field processing to see if contaminants are in some of the samples that you're collecting. And then we find that the Street View system can be really useful also for public health and exposure research. And then we have a number of instruments that can be used to collect air quality data as well. In addition to all that, we have field laptops that can be used for preliminary data processing. In the lab, we've got servers in our rapid facility that provide access in the short term post-deployment for data storage and then preliminary processing of your data. And we have data processing servers that you can access to do the structure for motion and then also deal with some of the really large data sets that come in from other instrumentation. So full range of instrumentation that you need, from collecting the data in the field to doing post-processing of the point clouds. And then, as I said, the data will also be transferred to Design Safe for long-term storage. The next few slides go through some examples of how you can use rapid equipment to collect data and what you can do with it. And I'm going to actually zoom through this. So this is the first example, which is actually a 2018 example, but it does a really nice job of highlighting the use of the equipment. These were data that were collected post-earthquake and tsunami in Palu, Indonesia. This shows you what the affected area looked like based on satellite imagery. This shows you what it looks like based on orthomosaic mapping using data that were collected from a high resolution camera that was drone mounted. So you can see that you get tremendous detail in the drone mounted imagery. And then using structure for motion software, it's possible to generate a 3D point cloud of the surface area. This is what that 3D point cloud looks like. And you can go in and you can take measurements and you can figure out what the elevation of the surface is, what the depth of the landslide area is, etc. And I really like this example because that's what the research team did. And so if you look over here on the right, this is showing you a cross section through a slide area. And the orange line is the post-earthquake elevation that was collected using the drone-based image data and structure for motion. The blue and the green lines are a couple of pre-earthquake surface elevations that were generated using satellite imagery and a couple of different data sets, essentially. And so it gives you some sense of what on average, what the surface was pre-earthquake. And then the red line is estimated bottom of the debris flow after the landslide, with the area between the orange and the red being the volume of debris. And so using these data, it was possible to get an estimate of what the debris flow or the volume of that debris flow and the area, the full effect of it, what it based on the preconditions and the post conditions. So really valuable information coming from those data that were collected just using cameras mounted on the drones and structure for motion technology. This is another example, which is looking at a large, this was post Hurricane Michael, also in 2018, and initial STEER field assessment identified damage to a lot of large volume buildings. A PI from Auburn wrote a rapid grant wrote rapid proposal, got NSF funding, and then the rapid team went into the field to support activities to collect information on these large volume buildings. This is showing on the right some of the data that was collected using LiDAR equipment. This is mostly terrestrial LiDAR. And this kind of gives you an image or the fly through of what those data look like. This is all highly accurate point cloud data. So you could go in and you could measure the size of that beam, you can measure the volume of the building. Using that data, the research team was able to identify the damage to these large volume buildings and essentially come out with the data showing that there was a common failure mode for 12 of these large volume buildings, and determining that there was compression from windward wall pressure and then bending due to uplift, and that was causing failure of these roofing systems. So a really productive project that started with the rapid steer going in very early, saying, hey, this looks like it might be an issue. This team writing a rapid proposal to NSF, taking the equipment into the field, getting data, and eventually coming out with a solution to the problem. This is another data set that came out of the 2025 LA wildfire fires. This image shows where data was collected in that fire area. So there were street view systems mounted to cars, and they drove all those blue lines that you see up in the top left. Then there was also high resolution digital and multispectral camera data, or digital and multispectral cameras used to collect data in that region that you see up on the top right. This is showing you some of the images that came out of that. You can see from these images that there is non-uniform damage patterns. I don't specifically see it here, but there were places where you could look and you could see that first responders had noted that electric vehicles, they would put EV on the ground, had been burned. You can certainly see the burn perimeter. You can see damage to vegetation. You can see the surviving vegetation, surviving homes. This is just another image showing similar data. And then recent work at the Rapid has used AI tools to go in and rapidly identify the level of damage to building structures as well as other vehicles, et cetera, other structures and other materials in the area. And this is just sort of emphasizing, this is a 3D point cloud, and the level of resolution is 2 centimeters on the pixels in this region. And so you can go in and you can take measurements of volumes, you can take heights of trees, the extent of overhang. It's pretty amazing, the accuracy of the resolution of the data. And then because we also use multispectral and hyperspectral imaging, you can go in and you can, from the hyperspectral imaging, pick out things that you wouldn't see with just the visible light spectrum. And so on the right is using wavelength to pick out some of the charcoal, highlighting the charcoal signal to make it easier to identify burn structures using AI tools or other rapid assessment techniques. Okay, so those are all the exciting things that you can do with rapid equipment. Next step. If you're interested, I would highly encourage you to participate in our summer 4-day training workshop. It happens in July when it's nice in Seattle. It's just a great opportunity to learn more about the facility and the equipment that are available. But there are also lots of 1-day, half-day trainings associated with a variety of events, etc. So we do a 1-day training during the summer as part of an ideal workshop. There's going to be a half-day workshop at the upcoming NHERI Computational Symposium. We do a 1-day workshop at ERI every year. There's a 1-day workshop supported by FEAR every year. And then if you are going into the field, we offer ad hoc training at the Rapid facility prior to your mission. And then you can certainly come yourself or send students to the Rapid facility post-mission to work on data processing. One last slide to encourage you to encourage your graduate students to apply for our Rapid Graduate Fellowship. It provides them access to Rapid equipment, training, $37.50 for in funding to support the work and a $1,500 travel stipend, and then up to $7,500 in wage, equipment, and staff support fees. So it's a great opportunity for them to go into the field, to get trained, to go into the field to collect data, and then work with Rapid staff to process their data. And with that, I will open it up to questions.
So our first question is, how can we use any of these equipment in our lab, specifically in another state?
So you can take the equipment almost anywhere. There are travel bans for drones in some countries, but if you want to use, if you have funding to use the equipment, then you should get in touch with our staff, or even if you're writing a proposal to use the equipment, you should send us an email, tell us kind of what you want to do. We'll put you in touch with the right staff people who can help you sort of finalize your equipment and staffing needs, and then put together a budget for the project. And at that point, you can basically take the equipment and use it wherever. If you need training on it, we can do some training remotely. You can come to the Rapid facility to get training on it. If there's a staff member, some of the equipment requires a staff member. There are drones that only our staff can fly. There's some other equipment that our staff need to be there. So our staff can train you and students in the field, etc. But the first place to start is probably sending an email telling us kind of what you want to do so that we can get you in touch with the right leadership team member and or staff person to help you finalize your plans.
Thank you. Another question says, thanks for your great presentation. Looking ahead at the next generation of natural hazards reconnaissance, are these specific emerging technologies, such as automated AI-driven damage detection or satellite integrated imaging, that the Rapid facility is currently looking to integrate into its equipment portfolio?
So we are definitely, as I said, we have a staff member who is supporting our AI activities, and he is actively engaged in working and using our data and developing AI queries, essentially, that enable rapid processing of image data. And a lot of that work has been done on the LA wildfire, or we'll say urban wildfires. And he's actually doing a presentation and a short workshop on that work at the Computational Symposium in a week, 2 weeks before that symposium. There will be other training opportunities associated with that, but yes, we're actively engaged in developing example AI applications that use data collected with Rapid equipment.
And then
I'll repeat it, Robin. I have it open now. So the question is, how do I figure out exactly what equipment I need to accomplish the work and how long I'll need the equipment? As I said, the first step is probably to write an email to the facility and kind of give some idea of what your interest is and what you want to do, and then we'll put together a couple people to talk with you and work, i.e. somebody who's got real expertise in exactly the kind of equipment that you're going to need to collect the data you want to collect, and then probably working with Jeff or Joe to put together sort of an equipment plan. Mike Grillo is also does those activities, and sort of work with you, talk through, figure out exactly what makes the most amount of sense in terms of time, money, and what your research goals are. There are opportunities to engage Rapid personnel as co-PIs, but it's unusual. Usually it is Rapid facility providing staff training equipment to collect the data and train students to do the data processing, and it's your project and you publish it. But there are opportunities to engage with Rapid faculty and staff, but it's pretty unusual. Our goal is really to help you do your research. Um, I think so the question is, are the data sets mentioned in the presentation published online? So the large volume data set large volume building data set is the Indonesian earthquake data. Those data are all available on Design Safe. I think the LA wildfire data are all published on Design Safe as well, although I'm not 100% sure. It takes a while to it does take a while to do the preliminary processing and get the data into a cleaned so that they're ready for publication. And then the PI whoever the PI was on the project that collects the data is the person who's ultimately responsible for publishing it. The Rapid facility tries to do everything it can to make sure that those data are cleaned and ready for publication as quickly as possible after they're collected. Any other questions? And I would encourage you to go to Design Safe and take a look at all the data that are available. Thank you, Maxwell. See, they are there. The data are published. Okay, well, there aren't any other questions. I will encourage everybody to keep their eyes open for maybe next summer's training event and come visit Seattle in July, which is a nice time to be here, and especially come and visit the Rapid facility. Have a good day.
Thank you so much. All right. So moving on, we're happy also to learn about the NHERI Large Mobile Shakers at the University of Texas at Austin and meet its co-PI, Dr. Brady Cox. Dr. Cox is a professor in the Civil and Environmental Engineering Department at Utah State University and co-PI of the NSF NHERI Large Mobile Shakers at the University of Texas at Austin, with a distinguished background that includes 8 years at the University of Texas at Austin and 6 at the University of Arkansas. Dr. Cox specializes in geotechnical engineering, focusing on seismic design and in situ site characterization. His groundbreaking research combines field testing with advanced computational analysis to improve subsurface imaging. He has led teams in gathering seismic data from significant earthquake sites worldwide and has worked on dynamic site characterization for critical infrastructures like nuclear power plants and bridges. Dr. Cox's accomplishments have earned him prestigious awards, including the Faculty Early Career Development Award from the National Science Foundation and the Presidential Early Career Award for Scientists and Engineers from President Obama. With over 170 peer-reviewed publications and extensive teaching experience, he is both a leading researcher and dedicated educator. Thank you for joining us, Dr. Cox.
Thank you. It's good to be here. I hope you can hear me okay. Great. I'm going to share my presentation. Just a minute. Okay. Well, thank you for inviting me to talk today to the Summer Institute. It's good to see a bunch of people out there listening, and hopefully I can provide some useful information as we consider moving forward with the NHERI program. So I am a co-PI for the University of Texas at Austin Large Mobile Shaker Facility. We call ourselves NHERI at UTexas, or the NHERI Large Mobile Shaker Facility. The PI for the facility is Professor Kenneth Stokey. Professor Stokey has been the PI of this facility for approximately 25 years. since the early 2000s when it used to be NEAS before it was NHERI. I've been involved with the shakers since they were developed at the University of Texas, also almost 25 years ago, although I've only been a co-PI on the facility since about 2014, so maybe the past 12 years or so. Patricia Clayton is also a co-PI for the facility. Patricia is a structural engineer. She's at Wake Forest right now. And then Professor Bob Gilbert, who's also at the University of Texas as a geotechnical engineer, is a co-PI on the facility. Perhaps the most important person to us right now is our site manager, Sung Moon Huang. Sung Moon graduated with his PhD from the University of Texas with Professor Stokey a few years ago, and he's our site manager, and he's the person that kind of handles our day-to-day operations for the facility. And we also have several great technicians not pictured here, Robert Kent and Alito Ruiz, who help us run our equipment. So just a quick outline of my presentation. I'll talk about our shakers and our associated instrumentation. And then I'll talk about one of our pieces of equipment that's somewhat new. It's called a Distributed Acoustic Sensing Interrogator, or a DAS IU. I'll talk about our science plan, and then I'll show you some example projects to hopefully spawn some thoughts in your mind about how you might be able to use our equipment. So this is our portfolio of our shaker trucks, at least. We have 5 large mobile shaker trucks. The ones that are highlighted up at the top in this orange outline, these are our 3 main shaker trucks. We have a truck called T-Rex. T-Rex is a triaxial shaker truck. As far as we know, it's the only one in the world that's operating. At the push of a button, you can transform it from shaking vertically to shaking horizontally inline or horizontally crossline. That's really unique functionality, and there's a lot of hydraulics and mechanics and electronics working together to facilitate this movement. And so it's kind of hard to keep a truck like this operating, and we've been able to do it successfully for over 20 years. So T-Rex is probably our most specialized truck. The truck in the middle at the top is called Liquidator. It's a low frequency shaker. So it really outperforms T-Rex at frequencies less than about 5 hertz. So at frequencies less than 5 hertz and down to approximately a half a hertz, Liquidator can output more force than T-Rex, but at higher frequencies, T-Rex can output more force than Liquidator. And so they're both on the same platform. They look somewhat similar to the untrained eye, so they sometimes people confuse them, but Liquidator has a single, much larger mass right here in the middle, and T-Rex is a little bit smaller mass. We have our urban shaker. We call it Thumper. Thumper can move around very easily. It outputs a lot less force than these other 2 larger trucks, and we can use it in cities and stuff without getting too much attention from people. It doesn't make people as nervous when this truck pulls up and starts shaking the ground. And so it can be configured to operate vertically or horizontally in shear. By the way, the Liquidator only operates vertically. Theoretically, we can transform it to operate horizontally in shear, but we've never done it before. It's quite a job to do it, and nobody has ever asked us to, so we haven't done it. We then have these other 2 trucks down here, Raptor and Rattler. And so these trucks are just other older Vibra-sized trucks that we acquired on donations from oil exploration companies or national labs. And Raptor can shake vertically and Rattler can shake horizontally. And then we have big trucks to haul these around with. We have field support vehicles, vans, instrumentation trailers, all kinds of stuff like that. On the back of our 2 largest trucks, Liquidator and T-Rex, we also have CPT pushing capabilities, so we can push cones and other instrumentation into the ground. In terms of our instrumentation, we have a lot of dynamic instrumentation. We have about 100 of these Smart Solo 3-component nodal stations. So you bury these in the ground or push these spikes into the ground, and they'll sense XYZ shaking They are each GPS synchronized, so there's no cables that run between them. A lot of people use these to put out grids of sensors on the ground surface, for example. We have this fiber optic distributed acoustic sensing interrogator, a DAS IU. These are really popular right now. A lot of people want to use these in their research. To purchase a DAS interrogator like this is somewhere between probably $150,000 to $200,000. So it's not easy for people to get access to a DAS IU. And so if you know what that's for and you're interested, we have one available in our equipment portfolio. We have lots of vertical and horizontal 1 hertz geophones. These have to be connected with cables. We have several hundred 4.5 hertz geophones and other 24 channel seismographs that you can use. And we have about 20 of these broadband nanometrics seismographs or seismometers, and with digitizers that you can use for recording aftershocks or horizontal to vertical spectral noise ratios, deep surface wave testing, stuff like that. We also have other dynamic signal analyzers and data acquisition system. We have load cells and accelerometers, and we have CPT equipment and liquefaction sensors that we're not showing here. A little bit more information about DAS in case there are people who aren't aware of the capabilities of DAS. So distributed acoustic sensing, essentially you have an interrogator that sends a laser pulse down a fiber optic cable. And that laser pulse or series of laser pulses that are traveling at the speed of light travel down to the end of the cable and back. And there's little imperfections in the fiber optic cable that reflect light back as the laser's traveling. And we record those reflected light transmissions. And as the cable stretches longitudinally, due to dynamic movements or even really low frequency, nearly static movements, we can sense strain along the cable. So the cool thing about DAS is our particular IU we can use to record a fiber optic cable up to 30 kilometers long, and we can have a 1 meter channel separation along that 30 kilometers of cable. So you can have essentially 30,000 dynamic sensors along the fiber optic cable, which makes it incredibly dense for spatial sampling. We can also sample in the time domain up to 100,000 hertz or kilohertz, 100 kilohertz, sorry. 100,000 hertz. So, and that's for gauge or cables that are less than about a kilometer long. As the cable gets longer and longer, you have to slow down your spatial sampling, or sorry, your time sampling rate, because you have to allow the pulse of light to go all the way to the end of the cable and back. And there's something called a gauge length, which is kind of like the average sensor sampling length in space. And we can change the gauge length in our interrogator from about 2 meters up to 30 meters. Here's some comparisons we've done at our test site in Austin, Texas, called the Hornsby Bend Test Site, where we buried several different fiber optic cables and then put horizontal and vertical geophones right next to the fiber optic cable. And down here in this plot, we're just comparing the signal that came out of the fiber optic cable versus the signal from the geophones. And so they're quite similar to one another, and we've published papers where we've shown that you can extract very similar waveforms and similar dispersion data, for those people that means something to, from fiber optic cable as well as from traditional seismometers or geophones. We have several open source DAS data sets that have been published on DesignSafe. So some people just like to have access to DAS to see what the signals look like. And so we've published 3 open source DAS data sets over the past few years that have to do with various subsurface imaging projects. So you can look these up in DesignSafe if you want and gain access to those. In particular, this one at the top is a really, really unique and extensive data set where we were using T-Rex to shake vertically and in both directions horizontally, and to record kind of like a grid of fiber optic cable that was jogged back and forth along a site. So this is a really nice and very well documented data set here as well. In terms of locations where we've tested in the world, this is kind of a map over the past, let's say, 20 years of everywhere where we've taken our equipment. So we've tested in a lot of locations as both part of NEIS back in the day and as part of NHERI since about 2015 or 2016. We have even taken the trucks to New Zealand, to Hawaii, some of our instrumentation to Taiwan and other places. So mostly we're going to deploy inside of the US, but we have deployed outside of the US as well. Oops. So this is kind of just, I'm going to go ahead and just start playing these little animations. Hopefully they'll show up over the Zoom connection, but as part of our science plan, we have three main focus areas. We focus on improved subsurface imaging, so being able to look at the subsurface in 2D and 3D. This is still quite challenging to do. What you're seeing here in the upper left is us dragging a series of sensors behind a shaker truck and trying to profile or image a levee, for example. So there's some challenges associated with doing this, and there's a lot of uncertainty at times in developing images of the subsurface, but that's one of the major things we focus on. Another thing that we focus a lot on is in situ nonlinear testing or in situ liquefaction testing, where we push sensors into the ground, typically in some sort of an array. For example, here, these red dots in this image would represent three-dimensional accelerometers or geophones that we've pushed in little cones into the ground. And then we have pore water pressure transducers that are shown here in blue. So we'll shake the ground and we'll measure the nonlinear soil behavior in terms of shear strain, modulus, pore water pressure generation. The last thing would be structural health monitoring, where we've done projects, for example, where we put instrumentation on a bridge and we shake the bridge in various directions, vertically and horizontally, and we monitor its response in both the linear and, well, we'll just say mostly the linear strain range to keep things safe. I have some example projects here listed. I'm not going to go through these in detail, but just to give you a snapshot of some of the types of work that we've done in the past few years. There's two awards shown here. Both of them have to do with subsurface three-dimensional site characterization using full waveform inversion or ambient noise tomography. So we've worked on these projects either using our shaker trucks or our instrumentation to develop three-dimensional images of the subsurface. This was some work that was done by Kim Tran at the University of Florida. And we put a grid of sensors on the surface, and then we shook in various locations around this grid of sensors to develop images of the subsurface and identify voids in karstic deposits. And then they went back and did some testing here, SPT sounding, and confirmed the presence of a void in this location. This is some work that was done on the Big Island of Hawaii. And this was a proposal that was funded not through CMMI, but through the EAR program, Geosciences, with the PI Lynn from the University of Miami in conjunction with the USGS. And they used 396 shaking locations along the Kilauea volcano, and they were looking to try and map the magma system beneath the summit of the volcano, and they used over 1,800 sensor locations to do this work. So in that case, we were primarily providing a source, but also some instrumentation for their work. This is a project that has to do with evaluating the liquefaction mitigation techniques of either microbial induced precipitation or microbially induced desaturation. So we've worked on several projects related to microbial induced ground improvement and trying to use these methods, our shaker trucks in the field, to test the veracity of these improvement methods. So pushing instrumentation in the ground in these areas that have been treated microbially, and then shaking the ground, ranging from small to moderate strains, and looking at the response of the ground in terms of the strain as well as the pore pressure buildup. Down here in the lower right, you can see that these blue lines are showing the unimproved P wave velocity. And this vertical line right here represents 1,500 meters per second. That would be the P wave velocity of fully saturated soils. And then you can see after treatment that the P wave velocity in some zones has increased and in other zones has decreased. And this target area down here, they were looking to try and desaturate the soil and indeed achieve that through some of the bio mechanics of the microbial induced desaturation method. So, and one of the things that we have tried to develop over the past few years is an ability to test deeper and deeper soil deposits. And so what's shown here is an augering system that we've come up with. And I can show you an example of the auger here, okay, where this is screwed into the ground. And we use that auger to induce shaking at greater depths. If we're just parking our truck and shaking from the surface down, we can't target as deep of soil deposits. But if we install one of these augers, we can push instrumentation down to greater depths, and then we can shake on top of the auger stem, and we can induce shaking at greater depths, and then we can build up strains at greater depths in the ground. So this is work that was performed with Diane Moog from Portland State and Ed Kavazanjian, two different locations, one of them on in Hawaii and one of them, I'm trying to remember if this one was up in Canada. I can't remember exactly. So I apologize for that. But anyways, one of these are some test results from Hawaii, and they were using different frequencies and shaking on the helical pile to develop in situ shear modulus reduction curves. And here's a line where they fit all of the measured data using the functional form of the model of Darandelli, but this is all in situ data that they're measuring in terms of shear modulus degradation as a function of strain. Some other work that's been done. This is a project from PI Mo from the University of Houston, where he was looking at developing these periodic metamaterial barriers. And these barriers are designed and constructed so that they essentially, what's the right word? Block, filter out frequencies that you can dial in according to the design of these elements. So you could target a certain bandwidth of frequencies that you would be able to isolate your building from, either in an earthquake or from, let's say, railroad vibrations or something like that. So part of this project was had a need to do some in situ testing to validate the functionality of these periodic metamaterial barriers. And we did that at the Hornsby Bend test site in Austin, Texas. Another project that we just wrapped up last year was with PI Alexis Alt at Utah State University. And this was interrogating what they call the earthquake critical zone. And there's a lot of pieces to this project, but one of the pieces was related to taking our big shaker truck liquidator to the southern San Andreas Fault near Palm Springs, California. And here's some pictures showing the installation of fiber optic cable across the San Andreas Fault. We installed about 1.5 kilometers of fiber optic cable. That costs about $1.80 per meter on average. But then once the fiber optic cable has been installed, you have essentially a sensor every meter along the cable. And we also installed a bunch of nodal stations, but every dot you see here, every 10 meters along this cable, we shook with our truck, and we also hit with a sledgehammer. And so there's some mapping where they had mapped the fault location at these blue lines here, but there were some instruments that were detecting creep or movement, and they were showing the fault was located in a different location. So we were there trying to identify where the actual location of the fault was. So we did some testing, using sledgehammers as well as several sweeps from our big truck liquidator. Hopefully this sound comes through and it's not too annoying. That's the sound our big trucks make. And what you see here is the truck moving, setting the base plate down in one of the testing locations, and then it's going to start shaking here in a minute. The first sweep we're going to run is higher frequencies. If you watch this line here, we can kind of see the truck starting to move. So that sound is pretty annoying to me, so it's probably annoying to you as well. So I'll skip through some of that. This is some of the output from our distributed acoustic interrogator, where you're looking at 1,500 meters of fiber optic cable, and this is one sledgehammer blow along the fiber optic cable at a distance of 700 meters from the beginning. And you can see how the waves are greatly attenuated on one side of the fiber optic cable versus the other. And that's because these waves are being reflected back by the fault. So just even by looking at the waveforms in the time domain, we can see the location of the fault. And what you're seeing here is an animation of every 10 meters the sledgehammer hits along the fiber optic cable. And you can see as the waves get close to these lines that have been drawn here, there's significant attenuation relative to the other direction. And then once the sledgehammer hits are on the other side of the fault, there's a much different pattern of the way that the waves are scattering. So we use that information to develop a subsurface image and locate the fault and look at the areas of creep and stuff like that. So these are some of the capabilities that we have with our equipment at the University of Texas. I'm happy to answer any questions. If you also want to reach out to our site manager, Sungmoon Huang, you can contact him at this email address, or you can send me an email as well. I'm happy to talk. So with that, I'll take any questions that you might have.
I think we have our first question in the chat.
Okay, I'm trying to find the chat. I might have to escape out of presentation mode. There we go.
While you're doing that, I'm just going to go ahead and read this one. What is the maximum depth that can be detected for subsurface imaging?
So it depends on the method of imaging that you're using. If you're doing something like traditional seismic imaging, like reflection profiling, you can look very deep, many, many kilometers. But the type of imaging that we're often doing with like full waveform inversion and three-dimensional imaging, we're typically profiling the top tens to 50 to 100 meters, something like that. And if we're doing surface wave testing, it's pretty common that we would be able to look down hundreds of meters, 200, 300, 500 meters even, with our trucks and instrumentation, but that would be a 1D type profiling. So in 3 dimensions, tens to 50 meters, let's say, one-dimensional shear wave velocity measurements down to hundreds of meters. And then if you're doing something like reflection testing, where you're really just getting an image of the subsurface without super accurate travel times, then that would be kilometers. You're welcome. Okay, so a question, do the large mobile shakers at the University of Texas have any local testing areas near Austin where researchers can run proof of concept or shakeout tests without needing to pay significant charges for mobilization? Yes. So we have a site at the University of Texas. We call it the Hornsby Bend site. Some of our open access data sets have been published at the Hornsby Bend site. We have CPT data that we've used for site characterization. We have boreholes. We've done downhole testing. We have fiber optic cable installed at the site that people can use. And if you test at the Hornsby Bend test site, you don't have to pay a lot of money to ship the trucks around the country. So depending on where you go in the country or in the world, it can cost tens of thousands of dollars to move the trucks around. But if you're able to take advantage of our test site in Austin, then you don't have to pay for those mobilization charges. So it's much more economical. And that was the site, for example, where Dr. Moe performed his testing of the periodic metamaterial barriers. Sometimes people will run proof of concept tests there and work out the bugs, and then take the show on the road to do testing where they actually want to do it.
Any final questions?
So there's a question here of how to decide the frequency range that will serve the purposes. So on our website, we have a plot that shows the frequency and force range of all of our shaker trucks. So you kind of need to come up with an idea of the frequencies that you're and the force levels that you think you might need. And then we'll pick one of our mobile shaker trucks that is going to match your needs. And we're happy to help with those types of discussions as well. So either Sung Moon or myself can talk you through kind of deciding which of our trucks and instrumentation will best suit your needs.
Thank you so much. In the interest of time, if you have any further questions, please reach out to Dr. Cox or Sung Moon, and they are happy to assist you. With that, we're going to move on to our next presentation. And so we are excited to present the NHERI Wall of Wind Facility and its PI and director, Dr. Arindam Chowdhury. Arindam Chowdhury is a professor of the Department of Civil and Environmental Engineering at Florida International University, where he directs the NHERI Wall of Wind Experimental Facility funded by the National Science Foundation. He holds a PhD in engineering mechanics from Iowa State University, a master's in structural engineering from IIT Mumbai, and a bachelor's in civil engineering from Jadavpur University. His innovative research in hurricane damage mitigation has influenced building codes and developed technologies to enhance coastal resilience. He holds 2 patents, including the aerodynamic mitigation and power system designed to harness hurricane force winds as a renewable energy. He has received FIU's Top Scholar Award and the Charles Penkow Award for Innovation from the American Society of Civil Engineers, as well as numerous awards from organizations such as NSF, NOAA, and the U.S. Department of Energy. Additionally, he is a dedicated educator, having created active learning courses in hurricane engineering and structural safety. Today, we will hear from both Dr. Chowdhury and WOW's research scientist, Hussam El-Sayed. So welcome, both of you.
Okay, so this is a wall of wind facility. We have an aerial image at the FIU Engineering campus. You also see the debris field and the wall of wind building inside the wall of wind. Also, we have the staging area where we build the models on the right-hand side of the wall building. It doesn't go to the next slide. Okay. Here are some close-ups of the wall of wind building and the staging area. We have flow management systems that can be used to simulate atmospheric boundary layer flows, which is realistic simulations of the natural wind. We also have rain nozzles that we can do wind-driven rain system. Based on the requirements of the testing, we can adjust these roughness elements to create different profiles. And we have a journal paper that details all the different profiles and the tolerance parameters that we can generate. a view of the turntable. We have a 16 feet diameter turntable here on which we can put models, and then we can change the direction of the model so we can study the wind direction effects on the models. Here is a video. Osam, can you play this? Robin, can you see the video?
We can see the video, but we don't hear it.
Yeah.
Wall at Florida International
Now we
University,
do.
the NSF-funded facility that enables researchers to better understand wind effects on civil infrastructure systems in order to prevent wind hazards from becoming community disasters. The NHERI WOW experimental facility is powered by a combined 12-fan system capable of repeatable testing and up to 157 mile-per-hour wind speeds. One advantage of the facility is the multi-scale and high Reynolds number simulation using 12 fans and a water spray system, which demonstrates the effects of wind and wind-driven rain. The 16,000 square foot fenced-off secure area enables researchers to plan and perform destructive tests for up to Category 5 hurricane wind speeds, using a wide range of equipment, instrumentation, and experimental simulation protocols.
At the end of the video. Okay. So what you saw here in this video is the uniqueness of the wall of wind in terms of basically full-scale testing, which is important so we can understand the failure modes, which it's not possible in scale model. So we can do large-scale and full-scale testing to understand the progression of damage. And what that tells us is like how we can retrofit the structure, how we can come up with various mitigation techniques, and also test the efficacy of those techniques. We have a team of full-time staff and faculty who supports the NHERI Wall of Wind experimental facility. Some of the details about the facility is like, again, as I mentioned, we can do large-scale open jet flows. Our wind field is 20 feet wide by 14 feet high, so you can put like full-scale structures or subsystems. And we can go all the way up from, let's say, 20 miles per hour wind to 157 miles per hour, which is a Category 5 wind speed. We have a turntable, which can be rotated from 0 to 360 degree to understand wind directional effects. And we had roughness elements and adjustable spires to simulate suburban, urban, and other exposures. And we can also do the wind and rain simulation to understand the water intrusion through buildings under high winds. Some picture of the staging area where we can build specimens, and then we can use a forklift to bring it to the wall of wind turntable and test those out. So we can prepare test models here for one project as we are doing testing for another project at inside the wall of wind building. Some pictures of the large scale models. It can be made out of plywood or plexiglass. On the right hand side, it's a nice picture that you can see. We have a base model, but then on the top of the roof, those are PV panels, photovoltaic panels with pressure taps. So you can also have large scale modeling of solar panels and understand the effect of wind on those panels. And you can study various parameters, including the pitch of the panels and various arrangements. And you can look at winds coming from various directions, including coming from the back, which produces some of the significant wind loads. We have unique testing capabilities. Again, we can go up to a Category 5 hurricane wind speed. We can do different scales. We can measure aerodynamic testing. That means we can measure pressures. Like here, you're measuring pressures on the solar panels using pressure taps. We can also do aeroelastic testing, where we can understand the effect of vibrations on the loading. We can do failure mode testing, as some of the things that we saw in the video, like a roof failing, a metal roof, panel vibrating and failing in fatigue, short-term fatigue. We can do wind driven rain simulations, and not only we can test buildings, but we can test scale model of bridges, transmission tile lines, photovoltaic arrays, also in full scale. We also have the downburst simulation capabilities for localized transient effects. We have done with Lehigh University real-time hybrid simulation, and we have a paper published on active model feedback. So that's another area that we can help the researchers with using real-time hybrid simulation. Some idea on the scale effects. So here you can see like most of the traditional wind tunnels can go up to a 1 to 100 or 1 to 50 scale on a low-rise buildings, but we can go all the way from a 1 to 100 scale, which is the top left picture, to a 1 to 50 on the right, and then 1 to 10 at the bottom left, and finally go to like a, also we can do a 1 to 6 building. So we can study the effect of scaling on the aerodynamics of the building and also the effect of the Reynolds number on these aerodynamic loading. Because we have a large turntable, we can understand the effects of the surroundings. So this is another research that was done here by other researchers. I think this was done by Dr. Gorley from Stanford University. So the middle building is the one where we are measuring pressures, and then we have surrounding buildings using foam blocks or other elements that produces the surrounding effect. So you can look at Venturi effects, you can look at flow acceleration, and those kind of things which are dependent on the surroundings of a building. So you can do these kind of large scale modeling using the wall of wind. We'll give you some examples on testing. So on the top left, you see an elevated house, which are done nowadays to let the flood run underneath so that it doesn't impact the building. And some of these have been shown to be of high performance. So on the other pictures, you're seeing like we are testing elevated house using load cells. So as we see the wind going across this building, some of the wind goes underneath in the crawl space, and you can see the effect of the elevation on the aerodynamic loading. And we are using load cells to understand. So on the bottom two pictures, one is the building is elevated versus the other one, it's on the ground. You can clearly see the difference in loading using the load cells. And many of these information have been used in the building codes to understand the loading on elevated houses. This is a project transmission tower system. It's again a scale model, but looking at effects on the lines on the transmission tower systems and also on the tower itself. We have accelerometers and strain gauges, and we can have also load cells. So this is an aeroelastic model of a transmission line system. We are testing at the wall of wind. Hussam, you can play the video maybe on the right-hand side. So here you can see the vibrations, and all the relevant modes of the structure are taken into account while we are doing the aeroelastic modeling. So the modes of the transmission lines as well as the modes of the tower itself, and we can understand the wind effects on these kind of systems and then come up with either code suggestions or also retrofitting methods. Full-scale solar panel being tested. The original structure was in Washington, Central Washington University. You can see the bottom picture, which shows the actual building, 3-story building. On top of that, we have the PV panels, and the red circle shows what panels we are simulating at the wall of wind. So now we have on the top pictures, we have a full-scale array of the solar panels, and underneath that we have the framing, and we have load cells, as you can see, and we are measuring the wind loads from various directions. So this gives you an understanding of the range of the testing that we can do. We can go all the way from a scale model with pressure measurements. We can test at different scales to understand Reynolds number effect and scaling effects. You can do aeroelastic modeling of, let's say, transmission towers, and then you can also do these kind of dynamic testing using the actual PV arrays to understand the effect, not only from the turbulence of the wind, but also the resonant effect created by some of the wind frequencies matching with the structural frequencies of the system. We can play this video. This is an interesting video on traffic signals. And because we can simulate these at full scale, and the wires and the signals themselves, you can see the wind speed increasing, and then we have aerodynamic instability that's being captured now. You can see very large vibrations, which leads to failure of the systems. So the full-scale nature of our testing can make these advancement of knowledge possible, because now you can learn how the system performs at full scale, and from there you can come up with various either enhancing the design or using retrofit techniques or mitigation techniques to reduce the risk of the damage. Is that a video you want to play? So this is okay. These are shingle systems, I guess. So here we are testing underlayment. We can test various roof components. As you can see here, I think the roof components are already damaged, the shingles, and then some of the underlayments are coming off. What that means in terms of damage is not only you expose the roof, but you have paths for water intrusion, because you're what we call the secondary water barrier, which is the felt, that's gone in various places, and you can have water go inside the cracks and the joints of the panels, and you can have water damage. So we can do these kind of studies as well. Is this a video? Yeah, it is. So here, what you're seeing is wind-driven rain. It's a little difficult to see, but we are impacting a window with shutter, and we are testing the effect of wind-driven rain on the window with and without the shutter. So we are seeing not only how much the load on the window can be reduced by the shutter, but also understand the effect of the shutter in reducing the amount of water that goes through a window. And one of the biggest damages or losses in hurricanes is the wind-driven rain. So even when there is no external damage, which can be seen, a lot of water can go inside defects and cracks of the building and cause a lot of interior damage. So at the wall of wind, you can understand the mechanisms for those kind of wind-driven rain damage. You can understand the effect of the retrofits here. So this is another building being tested, and when we test the weak side, it fails like this. But we can also retrofit this building with stronger roof-to-wall connections, shutter systems, stronger roofing components, and we can retest it to understand if we can reduce the risk of these kind of damage. And as we have the debris wall, we can catch some of this debris. This is a real-time hybrid simulation testing. I don't think this is a video, but again, here, go back. Here we are seeing a model that has actuators. And this model has a tower on the top, which can be thought as a communication tower on top of tall buildings. So here we are using real-time hybrid simulation, where we have also the actuators that's giving the correct displacement calculated by numerical models. So we have a numerical substructure being simulated somewhere else. And then we have the physical testing, which gets information from the numerical simulation and update the deformation, so we can understand the aeroelastic effect. And we can also study the effect of dampers to reduce the amount of vibration and the response to the building. So this is the one where we work with Dr. Jim Rickles' team at Lehigh. And there is a collaboration between Lehigh and Wall of Wind. So if you are thinking about real-time hybrid simulation using these two different facilities, one is the one at Lehigh that can do the real-time hybrid simulation, and the physical testing can be done at the Wall of Wind. You can combine them and do real-time hybrid simulation. And there is a very interesting journal paper that has been published, and we have more publications that are coming to understand how we have advanced the knowledge through these kind of collaboration. So this is a unique collaboration between different NHERI facilities coming together to solve a unique problem. This is the downburst of non-transient, non-synoptic wind. So let's see if we can understand. So as you are seeing those flaps on the other side, they open and we can produce downburst effect on these kind of buildings. Do we have a smoke video here? Maybe. Okay, so the next video is the one that will show the flow that's produced by the flaps. Okay, it's not playing. Okay. So this is also another system that you can use. It's called the particle image velocimetry. So here you can see like a picture where you seed the flow structure. That means you put seeding particles inside the flow, and then you shoot laser and understand the effect of understand the evolvement of the flow around the structure. So the green color shows kind of or implies a laser being flashed, and then you can see the particles. So as we are getting pictures of the particles moving along with the flow and the laser shining on it, you can have programs that can calculate how the flow develops around this structure. So it's a very advanced way of learning about the flows around a structure. And you can correlate these PIV measurements with the pressures or the loads on the structure. So you can kind of correlate the effect of the flow with the loads that these flow exerts on the structure. So you can do this kind of high or advanced PIV kind of testing to understand the flow effects on various kind of structures using the PIV system.
This is a video of the PIV.
So this is a video of the PIV. So we are testing, I believe, a plate, which is hard to see, but there is this window through which you can see still the laser. And we are again understanding the effect of the flow on a flat plate here. This was probably Dr. Chris Letchford's research, right?
Yeah.
So we have a flat plate that's supported by the side walls. And then we are shooting laser and understanding the flow on a bluff body using PIV system. So these are very advanced techniques of understanding the flow and also understanding the effect of the turbulence on the loading on the structure. Same similar kind of research, but on a different structure, wind turbine. This is done by Victor Maldonado from Texas Tech University. It's based on his career proposal. So we are looking at the effect of wind on the blades of a turbine. And then you can understand the tip vortices, which are often blamed for the inefficiency of some of these turbines. But if you can have different techniques of reducing the effects of the tip vortices, then your performance increases. So Dr. Victor Maldonado produced this almost like a full scale of a turbine system and understanding using PIV the effects of the tip vortices and various approaches of reducing the impacts and increasing the efficiency of these kind of turbines, which can be used for wind turbines. It can be used for gas turbines and other kind of helicopter propellers and things like that. So we're just showing you the breadth of the testing that the Wall of Wind can do, all the way from buildings to transmission lines to these kind of systems of turbines. You can look at more information through the website, and so feel free to ask questions if you have, once you look at these various information that's available there, and you can reach out to me or you can reach out to the staff of the Wall of Wind, and we'll be happy to answer your questions. And if you have ideas about your proposals that you want to submit to NSF using large-scale testing at the Wall of Wind, feel free to reach out to me directly. I'll be happy to review your idea of what kind of experiments you want to perform and give you my suggestions about what's the best way to put that in your proposal to make it more competitive. Also, if you want to submit your career proposal as a young faculty, please reach out to me, and I'll help as much as I can in terms of providing some guidance about how career proposals can be strengthened by integrating research and education, which is a big part of NSF career proposals. So whether you're submitting a regular proposal or a career proposal to any of the directorates of the NSF, you're more than welcome to contact us to get feedback about your experiments, about your testing, and how to strengthen your proposal. So with that, I think this is the last slide. Is that right?
Yes.
And we acknowledge, of course, NSF and the NHERI program for the funding, and we'll be happy to answer questions.
There's one question in the chat, and I know we're kind of pressed on time for this one. But what are the opportunities to visit the NHERI WOW EF in person?
Yes, I mean, you just need to write to me. So we are in the NHERI no-cost extension, so we don't have workshop funds, but we can come up with different other ways to arrange your visit to the Wall of Wind. So if you're interested in the Wall of Wind, just contact me directly and we'll find a way to make it happen.
Thank you so much. Any other quick questions? Again, thank you. I've included Dr. Chowdhury's information in chat along with his email. If you have any other questions, please do reach out to him. Thank you for being with us. We want to go ahead to our final presentation. We're thrilled to present the NHERI Wind Research Facility and its PI and director, Dr. Jennifer Bridge. Dr. Bridge is an associate professor in the Department of Civil and Coastal Engineering at the University of Florida and director of the NSF NHERI Wind Research Facility. She earned her PhD and MS in civil engineering from the University of Illinois at Urbana-Champaign and her bachelor's in civil engineering from Texas Tech University. Dr. Bridge's research focuses on structural health monitoring, smart sensor networks, resilient coastal infrastructure, and full-scale bridge monitoring. An influential educator, she teaches courses in advanced structural analysis and received awards such as the University of Florida Excellence Award and the NSF Career Award. Dr. Bridge has also participated in various professional committees and represented the U.S. in international disaster resilience workshops, demonstrating her commitment to developing resilient and sustainable infrastructure. Please welcome Dr. Bridge.
Thanks, Robin. All right. Okay, so hopefully you can see my screen. And I'll go ahead and get started. So I'm really excited to talk to you about the Wind Research Experimental Facility here at the University of Florida. And I'm also excited that I got to go after the Wall of Wind because they laid a great foundation for the kinds of work you can do in wind tunnel facilities. And I'll try to kind of highlight some of the similarities and differences. And also my goal is to convert all of you on this call who aren't wind engineers to think about how you can actually come and do wind engineering research. And I'll kind of highlight how we've brought some people over to wind engineering. And so even if you're sitting on this call, maybe you wanted to hear about the rapid facility at the beginning, but now you're kind of stuck listening to the rest of these presentations. Keep an open mind about what you can do in wind engineering. All right, so with that, just a little bit of background. I'm going to kind of follow the format of some of the other presentations and start by introducing our folks here. So I work alongside Brian Phillips and Kurt Gurley as kind of co-directors of the facility. One thing I want to say about the University of Florida is long before we had a lab-based facility, this program, and long before I was even part of the program, has a really long history of a variety of types of wind engineering research, a lot of history and field observations, which I'm not going to talk about today, but it's kind of baked into everything we do, going out and collecting data during landfall and hurricanes, as well as catastrophe modeling. So everything from field data collection to laboratory work to simulation, and really putting it all together. And we do everything from what we talk about, like basic science, what we're funded to do, from NSF all the way through really applied work that kind of makes its way into codes and standards. In terms of who you might interact with on a daily basis here, Ryan Cattarelli is our wind engineering technical manager, and he facilitates and helps support a lot of the projects that come through our facility. Scott Powell is the site operations manager, so he manages the lab. You'll work with him on scheduling and kind of, working out the feasibility and the details of your test. We have Ty, who's our instrumentation and controls engineer, a really big part of the success of our projects. And then Susan is our research and business administrator. And as with all the other facilities, we have tremendous staff, even beyond who you see here, that really make magic happen in the facility. I'm always kind of amazed at what they're able to put together. So some kind of overarching objectives of our facility is provide users access to advanced wind engineering experimental research infrastructure. And as with any NSF-funded research, we want the research to be transformative, and we support this type of research through state-of-the-art experimental resources, integration with high-performance computing. We've got, again, skilled personnel. We try to maintain a nice, safe facility, and all of our users that come here have really great things to say about their experience. And we really want to expand and diversify the wind engineering community. I wasn't joking when I said we want to convert, other types of engineers into wind engineers so that we can develop a workforce that serves society, so we can have a more hazard resilient infrastructure of the future, which is the overarching goal of NHERI. So I just wanted to highlight, just to kind of give you an idea of the researchers and where they've come from. We've supported close to 30 projects in our facility from users from all over the US. And I also want to mention that a lot of these folks, again, don't necessarily come from, kind of a typical wind engineering background. So we've got folks that come from earthquake engineering or computational fluid dynamics or atmospheric science, and they've come here to use the facility. And we also do projects that aren't NSF funded, FEMA, Florida Department of Transportation, NIST, NOAA, to name a few. So here's kind of some of the items that I was talking about in terms of, the research backgrounds. So over half of our PIs are from non-wind backgrounds. I also want to mention, I just kind of did a count recently. Arindam was mentioning career awardees. All the sites are really excited to support researchers by kind of new research scientists. And so, we've had 9 career awards that have used our facility or are currently using our facility. And that's something we're really excited to kind of develop the next generation of wind engineering researchers. The objectives of our facility, we want to reduce uncertainties in the entire wind loading chain, from kind of the atmospheric phenomenon all the way through how we design more resilient infrastructure that's going to impact our building code. So we want to enable experimental rigor in a boundary layer wind tunnel testing. And what you'll see about our wind tunnels, there's a tremendous amount of automation and control that allows for repeatability, high fidelity data sets. And we have a lot of flexibility because of the automation to control flow conditions in the wind tunnel, so we can produce better composites of data. We also want to kind of go beyond what a standard traditional wind tunnel can do. And Arindam talked about some of their capabilities. We have some of those as well, where we're able to simulate non-stationary, non-neutral flow fields that are characteristic of some really damaging impacts of thunderstorms and downbursts, and then quantify the impacts of those flows on both body aerodynamics and ultimately the building loads. And then even though we're an experimental facility, we exist also in service of computational wind engineering. You really need data, especially, with AI and machine learning tools. You really have to have the primary data on which to build your models. And so being able to provide those repeatable data sets that can inform computational modeling is a really important output of our facility. And if you're somebody that does work in CFD, as with all the other facilities, our data is available and online on Design Safe. And so if you're looking to do some validation or get started, even without dipping your feet into experimental work, we can also support that. And then we want to advance automation and design of hazard-resistant infrastructure, so promoting experiments to validate hazard resistance of emerging and automated design approaches. And I'll show you in a minute, we also support cyber-physical wind tunnel testing and structural optimization. And of course, machine learning is kind of baked into everything we do, not just the specific experiments we do, but even the control of the various components of the wind tunnel to ensure that we're achieving the flow conditions that we want. All right, so what is a boundary layer wind tunnel? So this is what you're looking at right here. We're kind of the person here inspecting the building in this very non-staged picture is, that's at the test section, okay? So that would represent your model. So we are a scale model wind tunnel facility, so everything we do is at scale. And everything in the wind tunnel is there to ensure that we have accurate simulation of flow when it arrives at the test section. So this is kind of your wind tunnel 101 here, where going from the left to the right here, we're generating the flow in a bank of 8 fans that generate the kind of bulk of the volume of the flow. And then that flow is conditioned through some honeycomb. We can induce some large scale mixing with Irwin spires. But then you see this development section that makes up the kind of majority of the length of the wind tunnel. And that's where we're essentially mimicking the terrain to develop the boundary layer so that by the time the flow reaches the test section, we've got the appropriate mean wind speed profile, the appropriate turbulence intensity profile, and even higher order statistics to ensure we're accurately simulating that so we can understand how it affects whatever it is we're testing at the test section. It could be building, bridge. I'll show you some other things we put at the test section that are kind of interesting as well. So the challenges in a typical wind tunnel, this terraformer has been something that's been more of a kind of a manual process, not the terraformer, but in traditional wind tunnels, you might kind of manually place these, have a few terrain conditions available to you. However, our terraformer is unique in the sense that we've got over 1,100 elements that come up out of the floor at the push of a button. In under 2 minutes, we can dial up these elements. They range in height from 0 centimeters up to 16 centimeters. You can orient them with the wide edge windward or the narrow edge windward, and it can be homogeneous, but of course you can also have heterogeneous configurations. And we have closed form solutions. So if you know the flow conditions that you want at your test section, we have a closed form solution to figure out what terrain, what configuration of the terraformer is going to allow you to achieve those flow conditions. And so what this allows us to do is very quickly move through a test matrix. So you have a lot more opportunities to kind of look at a continuum of flow conditions rather than maybe just like, an open, a suburban, urban type of terrain. So this is where a lot of our researchers are kind of exploiting the automation here to actually have very large test matrices that they can move through. The latest, this isn't the latest, it's actually been around for a while now, but kind of our more recent addition to the automation and flow conditioning capabilities in the wind tunnel, something we call the flow field modulator, or the FFM for short. Everything has to have kind of a cool name here. And this is an optional flow control capability. So if you can kind of see, it's just downwind of the main fan bank. So you're still generating the bulk of your flow with the main fans, but you can, if you want to use the FFM, you slide it in downwind of the main fan bank. And let me show you a better picture of what this looks like. This is 319 individually controlled fans. They have pretty high frequency response. You can run them forward. You can also run them backward. This really allows you to shape the profile of the flow. So instead of just having a typical neutral boundary layer profile, you can now have a gust front profile where maybe you have higher wind speeds down below, lower wind speeds up at the top. And we're still working on characterizing all of what this can do. There's just a lot of degrees of freedom with 319 fans, all individually controllable. And so while this is experimental capability we offer to our researchers, and we certainly know how to converge on a lot of different profiles, it's also an active area of research, and we welcome users that are interested in helping us kind of characterize and shape the control of the flow field modulator. So specifically, what does it allow us to do? So I already mentioned it allows us to achieve kind of simulation of non-stationary events. So these kind of like gust fronts that happen really, really suddenly, where you have like a rapid evolution of the flow and then, change it. So the statistics are not consistent in the flow, and you really want to kind of capture those peak gusts. You can see on the right, this is an example of a hurricane trace that's, again, I mentioned we've got all this field equipment that we deploy during hurricanes. We can now bring that back into the lab and replay it, scaled appropriately, of course, in the wind tunnel. So we're not just limited to kind of consistent stationary flows. We can actually play back different conditions in the wind. So this opens up a lot of opportunity in the types of testing you can do and really getting at realistic flow conditions as well. And then I mentioned the non-neutral flows, right? So this kind of gust front simulation, this is kind of showing how we converge on that gust front profile where you have that nose condition where you've got that higher winds, higher velocity down low. And then not just being able to simulate this, but now looking at how it impacts the built environment and how it impacts the loads that the building is experiencing. So a lot of our users are using the flow field modulator. It also allows us to kind of modulate the lower frequency component in the flow. So we're allowed to get, we're able to get kind of larger eddies. And so this is an open area of research and something that we really welcome our users to kind of co-create the science on this with us. All right, so the types of tests that we can run in our facility, I've kind of just generally outlined them here. They don't all fit into these neat buckets, but this kind of gives you an idea. The first is flow characterization. Maybe you want to come in and you don't even want to put a model in the wind tunnel, but you want to understand. I'll give you an example. We had a researcher, Sungwoon Jung from Florida State University, that was really interested in understanding how heterogeneous terrain conditions impact the flow. And so he took a lot of aerial imagery. He applied machine learning models to basically turn the aerial imagery into the appropriate terraformer configuration to really just understand how those heterogeneous terrain conditions impact the flow when it gets to the test section. He did ultimately put models in there as well, but a lot of times, with our researchers, they're going to come in and want to understand the flow before they even start to look at the impact on the model. In terms of the types of models that we look at, we have rigid models. This is where, these aren't flexible models, they're rigid, and they're representing the shape, right? The shape of the structure you're interested in, understanding the interaction between the flow and that model that allows us to characterize the forces on that structure. And so those are the pressure tap models. We can have up to 512 channels of pressure distributed around the structure. The other type of rigid model is the high frequency force balance. This is where we have a load cell at the base. We can measure overturning moments and base shears. The example that I'm showing here is as a model of a high-rise building. My colleague Brian Phillips did a topology optimization set of tests in the lab. It's more than a set of tests. This was like hundreds and hundreds of these models where you can see the topology of this high-rise building has different kind of cutout sections. And he was basically optimizing the topology against different design parameters. And he was kind of doing it in real time. So he'd test a model using the high frequency force balance test configuration. He would measure the base forces and overturning moment. And in real time, he was using a numerical model to come up with the next model that he was going to build. And these were all made out of like a high density foam that was machined with a robot arm. So it was really rapidly prototyped. So he could I don't know the numbers, but he could move through dozens of these models in a single day. And just to kind of give you an idea, most wind tunnel testing in a commercial setting, you have like one model of your high-rise building that costs, $25,000 or, $100,000, these are very expensive models and you get one shot. And with testing like this, you can move rapidly through not only different model configurations, but also different flow configurations. So it really kind of changes the time scale at which you can do these tests. And then Arindam mentioned also aeroelastic models. This is where you actually do have flexibility in your model and you're looking at the interaction between the dynamic response of the building and the flow. And so we can also provide those types of models as well. And we also have done a lot of work, my colleague Brian Phillips in particular, and Arindam mentioned that they've also done this at the Wall of Wind, but this is kind of a newer concept in wind tunnel testing that we kind of call cyber physical testing. And this is where you have actuated either components of your model or the model itself is being moved during the test. And so from right to left, on the left side of the screen, you can see a model where we're changing the parapet height. in each, you're not change. It's not like it's moving up and down during the test, but we can have one parapet height, run a few minutes of testing, change the parapet height, run a few minutes of testing, and it can all be done again very rapidly and in an automated way so that we can move through a lot of configurations to come up with the optimal parapet configuration for whatever it is you're trying to optimize. The test in the middle is, this is kind of where somebody said, hey, can we put a shake table on the wind tunnel? And this was several years ago. And we said, sure, let's try it. And this is where the building has a rocking motion that's being induced while we, of course, are subjecting this to the flow condition to try to understand kind of the interaction between the, crosswind motion of the structure and the interaction with the flow. And again, much like you heard in the previous presentation, there's a numerical model that's exists in the background that's kind of dictating for each time step how that building is being moved in the crosswind direction as it's subjected to the flow. And then on the far right, you can see an example of cyber-physical testing where there's optimization of the placement of these fins, again, to optimize the response of the building. And that's kind of done in real time to get the optimal configuration of those fins. I think in this case, it was to reduce the displacement at the top of the building for occupant comfort. So that's just some examples of the types of kind of general types of testing that you can do. I mentioned that we're also interested in kind of different types of models in the wind tunnel. So I've just picked out a few here. There's others I could have shown, but on the far left, this is hot off the press, we just put trees in the wind tunnel for the first time. So even if you're not a structural engineer, there's a place for you here. In this particular test, they had noted that these pine trees were more susceptible to disease after they were exposed to hurricanes. And so they got funding from the USDA to kind of subject these little saplings to some extreme wind conditions in the wind tunnel. And then they went and, on purpose, expose them to the disease to kind of see if there's a difference in how they respond. So that was a first for us, kind of a proof of concept set of tests. On the bottom right, Luis Zambrano-Cruzati, he's now at NC State University, he wanted to put sand in the wind tunnel. We said, sure, let's put sand in the wind tunnel. And he was looking at how the effects of, I believe in this case, the moisture content of sand dunes impacts how they erode under wind loading. So this is an example, not just of really cool science, but also of how our staff is really creative at making sure we can safely and not ruin our equipment, support some of these types of tests in the lab. And this one was really interesting. Up on the top right, this is more of a standard type of test, but I wanted to highlight it. This is following Hurricane Maria. There was interest in better understanding the speed up effects of the wind over the mountainous regions of Puerto Rico, because essentially what happened is they noticed a lot more damage than they anticipated based on the wind speeds that were recorded. And again, it was thought to be that kind of acceleration of the flow over the mountainous regions. And so as part of a FEMA project that led to a NIST project and honestly led to an NSF project as well, it's kind of a nice succession of projects. We put these kind of 1 to 3,100 scale topographic models of portions of Puerto Rico with our probes kind of right down in the topography to understand how the flow over those terrain features changed with the characterization of those features. So that was a really, again, fun and interesting project that kind of at the time stretched the capabilities of our staff to be able to do. So, and this is a cool close-up. So in the interest of time, I need to wrap up here, I think. So we also have some instrumentation. I mentioned the scanning valve pressure scanning system, up to 512 taps of pressure taps that allow us to measure the loading on the structure. We have displacement sensors, accelerometers. For flow measurement, we have our VectaFlow probe system. These are 12 probes that can kind of be positioned anywhere around the test section at different distances, different heights. It's all automated. So again, you can just kind of, pre-program how you want your instrumentation to be placed in the wind tunnel. And then much like FIU, we also have a stereoscopic particle image velocimetry system. This is where we have the laser that shines down over the test section. We've got the cameras trained on the laser. We seed the flow with olive oil, and we're able to do kind of three-dimensional time varying characterization of the flow with the PIV. We also do all sorts of in-house fabrication, both of the models and the components of the wind tunnel. We have this 3-axis CNC router that did, in this case, the foamed topographic sections, but it works in lots of different types of materials. We have 3D printers, and we have a machine shop that can work with you on your the models that you want to design. They're really skilled and creative at supporting lots of different types of tests. So if you work with us, this is much like all the other facilities. So I'm just going to go through this really very quickly. So you have a research idea, you contact us, we assign you somebody to work with, and we're here to help you develop your proposal. We've been paid to help you do your proposal development. So don't be afraid to leverage that. You get it funded by NSF. We help you work out your test plan. We help you work out a schedule. We have project planning meetings. We, for lack of a better term, we want to hold your hand throughout the process. We're not just kind of throwing you out there to figure it out on your own. You come in and do the tests. Our staff runs the tests for you, but we love having you and your students here to kind of oversee the process. All your data is transferred to Design Safe. And then we also are there to kind of help you, as you work through analyzing your data and helping you make sure that your results get published and disseminated. And then we think about the next time you want to come in. What's the next project idea? So again, we're here to support you in your research. And if you want to learn more, we've got a virtual tour on our website. And of course, you can contact me or Kurt or Brian, and we're happy to walk you through your ideas, even if you're not a wind engineer. So thank you.
Thank you so much, Jennifer. I have one question, which you've kind of touched on already. How much experience does a prospective researcher need in designing a wind tunnel experiment?
None. You just have to have a good idea. We've got, you have to have a good idea. What is it that you want to understand about how wind is interacting with something, right? And even if you think that something isn't traditionally what you'd put in a wind tunnel, we can kind of work through how we can feasibly do it to make sure that, it's scientifically sound and the research is good. But that's what we have Ryan, our wind engineering technical manager, here to do. And we kind of iterate until we come up with a plan that makes sense. And again, if you're writing a career proposal and, you're worried that the reviewers aren't going to, like that you don't have wind engineering experience, I can point to, probably half of our career proposal, I don't know half, but a large number of our career proposal, they don't have experience in wind engineering. And so, we provide that support letter. And I think, reviewers at NSF now understand what these NHERI facilities provide in terms of support for researchers. So you really don't, you just have to have a good idea. And then we can work out the details and figure out how to make it work.
Thank you.
Yeah. Robin, can I add something?
Of course.
Yeah. So Jennifer, thanks for the great presentation. So I just wanted to make sure that all the participants understand that, our facilities, we work together. So we have different capabilities. And for example, what Jennifer showed, like they are great on the terraformer and the flow modulation very quickly. We expertise on large scale. So always think about like a proposal where you can use both facilities to get the best out of both of them. Okay, so you can plan like that, and you can talk to both me and Jennifer to develop such a proposal that uses both facilities and get the best out of our capabilities. So feel free to also make sure if you want to do a research that can use like both facilities. So I just wanted to add that.
Yeah, thanks, Arindam. That's true. And we've also recognized when the Wild Wind is a better facility for what somebody might want to do, right? So we're kind of like, we're complementary in that sense.
Yeah, exactly.
I think there are 2 more questions in chat, Jennifer.
Do you have examples of users that are connected experience? Yeah, this is like the theme of my talk. Examples of users that don't have wind engineering experience. What was the process to get them ready? Yeah, so when somebody is coming in with, like Luis, who did the sand project, right? Like he's a geotechnical engineer, but he came to one of our workshops and he's like, oh, this is something that I could really, see putting in the wind tunnel. And so it's a lot more hands-on. The proposal development process is more hands-on. The design of the experiment is more hands-on. Our staff was more hands-on with his students, in terms of making it happen. But what I want to be super clear, especially for junior faculty that or maybe feel reluctant to ask for that, that's what NSF has paid us to do. So you are not like, that's part of what we're here to do. And to the question that was asked much earlier, would you be a PI on a co-PI on the project? I think it was asked of the Rapid facility, right? Like we're typically not co-PIs. We've already been paid to support your research. So, don't hesitate. I think I speak for all the facilities. Like, really don't feel like you're asking. That's what we've been paid to do. So it just, it's a sliding scale of how hands-on or how hands-off. We have other users they're on like project number 3. It's very hands-off. They know the process, but we're happy to be hands-on. Yeah. I
think
saw one more
Yeah.
question here. Yeah. With UF's flow field modulator capable of simulating non-stationary, non-monotonic flow fields such as downbursts and gust fronts, what have been the most surprising insights regarding how bluff body aerodynamics and building surface pressure distribution change under these brief, high-intensity wind events? I don't have the answer to that right. So we've been spending a lot of time just being able to have the capability that most of our FFM projects have been in the flow characterization stage, but we do have hot off the press research from like Pedro Fernandez Caban has used this. And so I can direct you to some like recent papers on this, but I don't want to actually delve too far into trying to explain the results. I wouldn't want to speak out of turn, but yeah, I can get you resources on that if you contact me.
And I will put her contact information in here to make it easy for you. Any other last minute questions? I want to thank all of our speakers so much for being here today. I really appreciate the time and the effort that you have put into your presentations, as well as answering questions and just making yourself available to all of the early career faculty who are here today. So again, thank you so much. As a reminder, we will be sharing this presentation on NHERI Design Safe website, probably the Summer Institute page, as well as the NHERI ECO YouTube channel. We invite you to complete a short survey, which will be sent out via email. And then in an additional email, we will also be sending out the link to the facility flyers, the facility presentation, and the lesson plan, all which provide additional information to you about the 4 facilities that we have seen today. Inside of that, you will also find the contact information for all of the NHERI speakers for this entire webinar series. So we invite you again to look at the other sessions if you were unable to attend them, and check those out and see if there's any facilities that you are also interested in. And again, we thank the NSF for funding NHERI across the board. And with that, I'm going to just check chat one more time. Thank you again. We really appreciate all of your attendance and your questions. And thank you so much for your interest in NHERI.